allocca.
Thank you very much. So, first of all, thanks to the organization for inviting me to give this talk about gravitational waves and everything we know so far. I am Annalisa Locca. I think it was presented like I'm Annalisa Locca, I work in Virgo, and something like this, so it's correct. It's useless to repeat it. And what I'll try to do tonight is I'll try to drive you, to tell you this story, which, let's say, officially started on September the 14th, 2015, but actually it started, let's say, 1 century before, with in this date, we had the discovery, the first discovery ever of gravitational waves. And so Einstein was right. Why Einstein? Because gravitational waves were foreseen by the theory of general relativity of Einstein. So in this talk, so let's divide it in 3 parts, more or less. In the first part, I'll try to explain you what gravitational waves are, what they are produced by, what's the effect on the matter, and so how we detect them and what we detected so far. Okay? So let's try to understand what are these famous gravitational waves. As I said before, they were foreseen by the theory of general relativity, which Einstein published for the first time in 1915. He presented it for the first time to the world, to the scientific academy, Prussian Scientific Academy. And this theory, at the beginning, it was really hard to prove that it was correct at that time. So there were just few experimental evidences that it was correct. And also, mathematically, this theory was really difficult, was really huge. So the diffusion of this theory was also hard, because for people it was hard to approach these very difficult mathematical equations. But then, mostly towards the end of the 20th century, there were more and more experimental evidences that this theory was correct. And among these, also the discovery of gravitational wave. So Einstein's theory is a revolution in gravitation. That's why I put this title on the top. Why a revolution? Because the conception of the idea of gravitation before was not completely different, but there were some few crucial points which were completely rejected by Einstein and changed by Einstein's theory. And so before Einstein, like before Christ and after Christ, we can say in gravitation, before Einstein and after Einstein. Before Einstein, in the physics, the way to explain gravitation was Newton's law, which was characterized by a few points which were changed by Einstein's theory. So first of all, space is flat and absolute, and time is absolute as well, and it's something completely different from space. So you have space and time absolute. And in this space-time, the gravity is seen as a force between 2 objects, 2 masses. So one object is exerting a force on the other, and vice versa, and this force is proportional to the masses, the distance, whatever. So this was the vision of Newton's gravitation theory. And gravity force, at the end, gravity force was an instantaneous force, was not something which propagates in time, but it's something instantaneous. And this is something which is completely changed in Einstein's theory. Why? Because space and time become aspects of the same thing. So they are interconnected, and they form this 4-dimensional space-time. And this space-time is bent, is influenced by the presence of mass and energy, as we will see later. And because of this curvature of the space-time, we have the motion of masses in the universe. So that's the main difference with respect to before. It's not having objects in the space separated from each other, which attract each other with a force, but it's the space itself which forces the masses to move in some particular way. And finally, gravitational field is not something which propagates instantaneously, but has a finite speed, which is the speed of light. So far, we can still say that it's the speed of light. So to better understand this idea of four-dimensional space-time, let's try to imagine it like, to imagine the space-time as a fabric. So we have this fabric, and we put on it a mass, which is heavier and heavier and heavier. I think you saw in the exhibition something like this. So you saw this thing when you put the masses and there is a deformation. So this is the way it works for the general relativity theory. And so the more dense the mass, the more the curvature is increased. So here you can see a small animation, and that's an idea of how space-time is curved by the presence of the mass. So when you think about the masses in the space-time, don't just think about the big stars in the universe. Also us, we are masses, we have mass, and so we are also curving the space-time. Not just think about very big and very huge thing outside there. It's also us, we are doing exactly the same effect. Yes. Okay. So this is the only equation I put here. I don't want to go and solve the equation, don't worry. It will take forever, but it's not the aim of this talk. But anyway, I put it here just because it is beautiful. I find it really beautiful. Beautiful because it's a very compact, as seen like this. It's a very compact equation, and on this side of the equation, there is a term which accounts for the geometry of the space-time. And on this other part of the equation, there is another term which accounts for the mass-energy distribution of the space-time. And the better way to read this equation, to comment this equation, is this sentence by Wheeler, which is matter tells the space how to curve, and the space tells the matter how to move. So that's the better way to explain what general relativity is with respect to the past, to before. Okay, so in the end, after this introduction about general relativity, what are these gravitational waves that we are talking about? And so gravitational waves, you read the definition everywhere, which are ripples in the fabric of space-time. Now, I think after this introduction about space-time and so on, maybe it makes some more sense that imagine that you put on this space-time, you put a mass, you throw a mass, and the space-time will just have these small ripples propagating all around. So that's the idea of what gravitational waves are. And more in particular, if this works, we can see more. Okay. So in particular, they are deformation of the space-time. They propagate at the speed of light, were predicted by Einstein in 1916, and they can travel billion light years without being absorbed by the matter. That's the most important thing, because in this way, we can have gravitational signals also from very far away in time and space. So, once we know what are gravitational waves, let's think about what are they produced by. So as I said before, we are curving the space-time. We can make also gravitational waves. I'm making now gravitational waves while moving, while speaking, because every source which is not symmetrical produces, and as an accelerated source, not symmetrical, produces gravitational waves. So acceleration is easy to think. You have something which starts from 0 and then takes some speed, which is not constant. That's an accelerated body. And so everything which is not symmetrical, which has an acceleration, produces gravitational waves, produces ripples in the space-time. But, of course, these kind of sources will never have detectable effects. If we really want to detect these effects, we have to take masses which are bigger and bigger, heavier and heavier. And that's why we say that usually the astrophysical sources are the usual sources of gravitational waves. And so we can think about every kind of catastrophic event in the universe, like supernovae explosion, neutron stars colliding, collision, black holes spinning around and then falling into each other, and so on and so forth. So all of these catastrophic events are all good candidates to produce detectable gravitational waves. Okay, so here we make an example. So imagine to take coalescing binaries, which is a system of two stars, which could be neutron stars or black holes or whatever, a mix of the two. And they spin around each other, or let's say around each other, and then fall into each other and make one single object. And they produce gravitational wave in this process. In particular, this is a video. Now, this is a movie. Now we will watch it. And in particular, we distinguish three phases. The first phase is this called the in-spiral phase, in which the two masses are just going one around another, and so on and so forth. And they go closer and closer, faster and faster, up until they merge. At some point, you will see that they will merge in one single object. And then there will be some ring down, which means that the final star will still will keep spinning on itself. Okay? And this process, along the whole process, there is the production of gravitational waves, as you could see from this movie. So in this, if you want to see how the signal looks like in time, it's called a sinusoidal signal. So a sinusoid is just a kind of wavy signal. So it's something like this. And the signal, this is a model, of course, and the signal looks like this. So it's something oscillating because you see something which makes whoo, 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 and that's why you have an oscillating signal. And then, during the merger phase, which is when the stars fall onto each other, you have a higher speed, a higher frequency, higher amplitude, and the signal becomes louder up until they merge into each other, and then there is the ring down phase, which you can barely see because it's very tiny. So if you take this signal and you put it into a synthesizer, you can also listen the sound of gravitational waves. That's why we say listening to the whispers of the universe, because gravitational waves are whispers from the universe, and we can try to hear this sound. So in the first part, we just hear some kind of noise because the signal amplitude is pretty low. Okay, and that's an example of whisper from the universe. As I said before, this is a simulation, it's not a real signal, although we will also hear the real signal later. And so this signal is called chirp, because it's like the chirp of the bird when there are the bird doing chirp, chirp, chirp. This is the sound is very similar to the bird sound, and so that's why it's called chirp. Okay, the microphone we don't need. So, okay, we understood where they're produced and what's the wave shape, and so what's the effect of gravitational waves on the matter? So imagine that we have this setting of bolts in a circular arrangement. The effect of a gravitational wave, which is traveling towards the screen, so in this direction, perpendicular to the screen, is to deform the space-time in one direction and the other. So that's why Einstein here is deforming and becoming longer and then fatter and shorter. And this can happen in two different ways. One is called, these ways of deforming are called polarization. They are properties of the wave itself. And there are two kinds of polarization. There is the X polarization and X and plus. And this is pretty clear why they are called X and plus, because the deformation is a kind of plus, and here the deformation is a kind of cross. Okay? So here we see, again, the same arrangement of bolts and the gravitational wave passing by. You will see what happens to these bolts. Here on the top, the gravitational wave. and that's the way the matter oscillates when the gravitational wave passes by. So again, also us. It happens also to us that we squeeze and stretch in one direction and the other. It's something so small that we cannot feel it, of course. So again, can we become slimmer and taller with gravitational waves? It's difficult because the effect is really, really small. So how small is small? Imagine that we have two of the balls that we saw before, and these two balls are the distance between these two balls is stretched by the gravitational waves. So we have the new distance, which is this one. And the difference, the induced variation, so the difference between the old and the new distance is proportional to the amplitude of gravitational waves, so how big was the sinusoidal signal, and to the distance itself between the masses. So to give you an idea, let's imagine that we take two big black holes which make this gravitational wave and blah, blah. So the typical amplitude is of the order of this number, 10 to the minus 21, which produces an effect very, very small. If you put two masses at kilometer distance far away, the effect is of the order of 10 to the minus 18 meters, which, I mean, these numbers will not tell you anything. It's just a number on the screen and will not tell you anything. But imagine that this change, which is produced, is similar to a with-air change in the distance between the sun and the nearest star. So you have two stars far away, you measure the distance, and gravitational waves will change the distance between these two by an air width. And this is what we want to detect. Maybe even better if we have a comparison with the atom, for instance. This is a hydrogen atom, and here on the top, this is a movie, and here on the top you will have the order of magnitude, so 10 to the minus 10, 11, 12, and so on and so forth. And you will see with respect to the atom size, how big is the effect of gravitational waves. No, this one. Okay. So 10 to the 10, and then zoom in, zoom in, zoom in, zoom in. And finally, we get to this number, which is 10 to the minus 18 meters. And so this is something very, very, I mean, it's kind of impressive. And maybe it's even more impressive if you do an experiment yourself. It's like if you go to the sea, you want to measure the sea level. And then you want to see how much the sea level has changed when you pour a glass of wine into it. This is the kind of difference that you want to measure, okay? So that's why it's so challenging to discover gravitational waves, and that's why it took quite a long time. Also, I didn't tell you, but Einstein himself was not sure about the existence of gravitational waves. So at the beginning, he made these calculations in 1916, and he found that one of the solutions of his equations could be gravitational waves. And then he changed mind. He said, no, it's not possible. It's not possible. It should be wrong. And then he changed mind again and again. So it took a few years for Einstein to convince himself that gravitational waves were really existing. So, how do we detect such a small effect? How can we do it? So what we do is we use a tool which is pretty ancient, actually, because it's an interferometer, a Michelson interferometer, which was an instrument which was used by Michelson and Morley in 1887 to try and measure the ether. And so in the past, it was people thought that electromagnetic wave could not travel in empty space, but there should be some material which allowed the waves to travel. And they thought this material could be this ether, which was everywhere. They tried to do this measure to show whether the ether existed or not, and the answer was not. And from that point on, people said, okay, gravitational waves can actually, electromagnetic waves can actually travel in vacuum. So we use the same kind of instrument, which is an interferometer. And this is our interferometer, Virgo, which is in Italy, and in particular is in Cascina, which is near Pisa. I think everybody knows where Pisa is, or what this is. Virgo is an interferometer of Michelson, just the same principle, but just with a little difference, which is 3 kilometer arms, so not a pocket size kind of interferometer. And so, of course, there are many, many more differences, but the basic principle is exactly the same. Virgo is a collaboration, a European collaboration, and there are laboratories from all over Europe. So how does an interferometer work? This is some lesson of physics. There is a laser, so a laser beam, which impacts on a mirror, which is partially transmittive and partially reflective. So this wave is split in the two parts of the, sorry, this is going on its own, I'm sorry. So this beam is split in two parts. And then these two parts are called arms of the interferometer, like the arms. And then at the end of each arm, there is a mirror. So the light beam is reflected back. They come back on the, I'm sorry, it's going, I don't know why. The two light beams go back on the beam splitter on this mirror, and they recombine and they sum up. And they do what is called an interference. So now, what is an interference phenomenon? Interference is something really easy. We have two ways, and they can be in different conditions. They are called phase condition with respect to each other, which means the top, the highest part, and the bottom part of the wave, they can be either coincident with each other, in this case, or they can be in opposite phase. So the bottom of one wave corresponds to the top of the other wave. And so we have two different, let's say, configuration, and all the configurations in between, because they can be in any random position. So if two waves in this condition sum up, they make what is called the constructive interference, and we have more light at the output of the interferometer. But if the two waves are in a counter phase, so they're not the same phase, their sum will be zero, because the top and the bottom sum to zero. And so this means that there is no light at the output of the detector, and this is called the dark condition, the dark fringe condition. Okay, so what we do is we keep our interferometer fixed at the dark fringe condition. And what happens to the interferometer when a gravitational wave arrives? So we have the same image as before, but now we put the interferometer inside. And so when the gravitational wave arrives, the arms of the interferometer will change length. So we'll change length in a differential way, which means that one becomes longer, the other one becomes shorter, and vice versa. And in this way, the interference condition of the two beams at the output of the interferometer will change. So we keep the interferometer fixed at one condition, which is dark. And then when gravitational wave arrives, the length bit of the arms will change, so the interference will change, and we will have light. But now all of this is explained here, so it's more clear, okay? Okay, so the laser beam starts from here. The beam splitter splits into the two arms. This is one of the arms. At the end, there is a mirror. The light is reflected back, and they go back here on the beam splitter mirror. They recombine, they sum up in a destructive way. And so, in the end, there is no light at the output of the interferometer. But then when a gravitational wave arrives, it will change in a differential way the arm's length, and there will be some light at the output of the interferometer. So this is the kind of effect that we want to see, that we see in our detectors. Okay, is it clear? Are you already like dying? Are you awake? Okay. Okay, so this is just, let's say, a frustrating slide for people who work on the instrument and have to to really make it work. But I mean, it's frustrating for everybody who works in this field, which is the noise. So noise is the most offending thing in all the experiments, and in particular in ours. So what we want to do is to reduce noise more and more and more in such a way we can detect this small signal, because you understood how small it is. So to give you an idea, imagine that you are in a party, you're at a disco with all the music and people chatting and people singing and whatever, and you want to hear what one particular person is saying in this noise, in this mess, in this party. So that's the kind of thing that we want to do. And so just to give you an idea of the noises, what kind of noises are talking about? There are, of course, so many noises. I will not even go through all of them to explain what they are, but just give you an idea about the seismic noise. So seismic noise is not earthquake. It's not that we have to wait for the big earthquake which destroys everything. No, it's the usual noise that we have on the soil. So this kind of noise is 10 orders of magnitude bigger than the kind of effect that we want to detect. And this is just one among all the noises that we have and we want to fight against. Okay. So, okay, you saw the interferometer on the paper with this wave and so on and so forth, but an interferometer is quite different. It's a very sophisticated instrument. Here I just put some few slides just to make you understand that it's not a thing on the paper. So I will not explain you what these slides represent, but it's just to make you have the curiosity to come and see our site, to come and visit our site. So you will have a tour and you will understand what these things are. So it's a good thing to do when you come to Italy and come to Pisa to see the Leaning Tower. So, how do we detect? Okay, we are not alone. We are not the only interferometer, as you know. And why we are not the only interferometer? For different reasons. Interferometer is like a microphone. So if you have a microphone and there is some sound arriving, you catch the sound, but you don't know from the sound of the microphone where the sound is coming from. What if you had one microphone here, one there, and the sound is very close to this microphone? You can localize where the source of the sound is. So with many detectors, it's much easier to understand where the gravitational wave comes from, because from the okay, no, go back, okay. Because from the amplitude of the signal and also from the delay of the signal from between each other, we can understand in which part of the universe, from which part of the universe this gravitational wave comes. There is also another reason, which is, imagine that in one of the detectors we have a signal, or we think we have a signal, but nothing in the other detectors. So it's most likely not a real signal, but it could be a fake, because maybe there is some noise that we didn't control, and so it's not detected by all of the interferometers, and so maybe we just have to discard this signal, not as a gravitational wave signal. Okay, so the most famous partners that we have, I think you all know. These are the LIGO interferometers. There are two interferometers which are in the United States. One is in Livingston, which is in Louisiana State, and the other one is in Hanford, which is in Washington State. And as you all know, 3 members of the LIGO Virgo collaboration were awarded with a Nobel Prize in 2017 for the discovery of gravitational waves. And at the moment, there are 4 detectors online at the moment, the 2 LIGO detectors, Virgo, which is here in Italy, and then there is another small detector which is called GEO 600, which is a detector with a 600 meters arms long, And this detector does not have the same sensitivity as we have, but they do a lot of technological research, and we also use their technological studies to improve our sensitivity. And then, at the moment, this lives on its own, this guy. Huh? No, I'm sorry, can we go back? Back? Okay. Bye-bye. It's fine. So at the moment, we are in what is called the observation run. So observation run means we are all online, and we take data. We will take data for 1 year from we started on the 1st of April, and maybe we will finish on the 1st of April, or maybe we will finish later. But the most important thing is that we are taking data all together. And then in the future, there will be 2 more interferometers. One is Kagura, which is in Japan, is an underground detector in Japan. And this is almost finished, and they will join the observation run by the end of the run. And then there is Indigo, which is at the moment still a project, but it has been approved by the government, and they are a partner of LIGO, and they will join soon the network of detectors. Okay, so these are the detectors which detected the gravitational wave signal, but this is the first black hole detection ever. This is how the signal looked like in the 2 LIGO detectors. So these 2 gravitational waves, these 2 black holes were 1.3 billion, this event happened 1.3 billion years ago. And if you make the comparison with the Earth in that moment, okay, so since the gravitational waves travel at a finite speed, so they are not instantaneously propagated, what we saw in this event were produced 1.3 billion years ago, which is when on the Earth the multicellular life was starting developing. So they come from very far away in time and space. And okay, there were 2 huge black holes, 30 solar masses each, not exactly 30, but very close, 29 and 36. But 30 solar masses means that you put together 30 suns, the mass of 30 suns, you put them all together and you squeeze them in a radius of like 100 kilometers or so. It's something really crazy, because your mind cannot even imagine what it means to have such a huge mass in such a small circle, in such a small sphere. So it's something really impressive. And these objects were traveling at a very high speed, at something like 60% of the speed of light, which means that if you make the comparison, it's like going from here to the moon in 10 seconds. So again, these big, huge objects traveling so fast with such a high mass. And this is what produced the first gravitational wave that we detected. And here we have a movie, again, of this gravitational wave signal. What I want to underline here is also the time, because all this process that I just described happens in less than 1 second, okay? So here you have the 2 black holes. Here you have the space-time, which is curved by the black hole masses, and the colors represent how the time is slowed down by by the black holes. So here you have the gravitational wave that is produced by this movement of the black holes. You see that it is highlighted over and over. And at the very end, we will have the merging phase, which is something also very difficult to predict and to model, because there are very extreme conditions in this phase. So they finally merge. Okay, and they become one single black hole in the end, and the ring down phase and the propagation of gravitational waves. So that's a simulation, of course, of the signal, the first signal that we detected. Okay, now I told you that I was going to make you listen the sound, the real sound of gravitational waves, and now we will hear the sound of gravitational waves. It will be repeated 3 times, but always the same sound. Okay. you can barely hear it maybe, but it's something like whoop, whoop, whoop. It's the usual chirp that we had before also. And that's the real one. Again, it's not that we really hear the sound of gravitational waves. It's just if you put this signal into a synthesizer, this is the kind of sound that comes out. Okay, so just to give you an idea about the masses and energy in this story. This is another event, what I'm talking about, because as you know, we detected more than one event. This is the this is another event. What you see here, this name, this is the day where the gravitational wave is detected. So 17 is 2017, 01 is January, 04 is the day, okay? This is the way we name gravitational waves. And then if there is more than one per day, it will be A, B, C, and so on and so forth. So this system had 31 solar masses, the first black hole, and 19 solar masses, the second black hole. And after the final black hole had 48 solar masses, which means that there is something missing. There are 2 solar masses missing. And where are these solar masses? So, you know, another reason why Einstein is very famous, more than the general relativity, is his picture at the breadboard with E equal to mc squared. Of course, he was not writing that, but this is one of the most common pictures of Einstein that you have in the network. So there is an equivalence between mass and energy. So whatever is mass has an equivalent in energy. So it means that these 2 remaining solar masses were just converted in energy. But energy of what? Energy of gravitational waves. So these two solar masses which are missing in the count were converted in the energy, which is the deformation of the space-time, which is traveling in the space-time. And that's something else which is difficult to understand, because we don't really know what it means to have energy embedded in the space-time. But that's the way it is. So to give you an idea again of how much is this energy, so you take 60-watt light bulbs, and you need this many, which I cannot even read. I mean, I could stay here forever to read all the zeros. So this many light bulbs to make this much energy. So that was the energy converted into gravitational waves. So finally, Virgo enters into the game, because so far the first event which was detected only by the LIGO interferometers, because Virgo was still, there was still work ongoing on the Virgo interferometer. But then we entered online and we detected this first triple coincidence, which means all the 3 detectors detected these gravitational waves. And what was important here is that thanks to the Virgo detector, it was easier to understand, for the same history of the microphones, it was easier to understand where the provenience of the signal, where the signal was coming from. And here you can see the signal in the 3 detectors. So this is another movie, and so far we have talked about gravitational waves by black holes, produced by black holes. And as you can see here, the longest event lasts less than 2 seconds, okay? But now we are going to see what is, compared to this, the length of a gravitational wave produced by a binary neutron star system, which is something different for the masses which are involved into this process. Okay, now we can stay and talk about our life, our things, because it will last a bit long. So you see how it becomes shorter and shorter with respect to this gravitational wave. Why is it so? Because here we are talking about masses of the order of 30, 40, a lot of solar masses, but here we have much smaller masses, which can be order of few solar masses up to 3, maybe solar masses, 2 solar masses or so, okay? Now we will hear the sound as well at some point. You see, it's still going. Okay, there we go. Okay, and this system as well was, this signal as well was detected by the 3 detectors at the same time, so Virgo and the 2 light detectors. And thanks to this event, we can set the starting point for what is called the multi-messenger astronomy, which is something, a completely different way of making astronomy. Why? Because it doesn't it involves, of course, the gravitational wave detectors, but also it involves also the telescopes and the neutrino detectors and the gamma ray detectors, radio wave detectors, and so on. So why is it like that? The reason why black holes are called black holes is because there is nothing which can go out of it, because the gravitational attraction is so strong that not even light can escape what is called the event horizon, but we don't care. So the hole in the fabric of space-time is so deep that not even light can escape this, hole. That's why it's called the hole. That's not the case for neutron stars, because neutron stars also emit electromagnetic radiation that we can catch with telescopes and instruments like this. This means that black holes can only be seen so far directly with gravitational waves, but neutron stars, binary neutron stars, can also be seen by telescopes. And we can make a new astronomy. Why? Because in this way, gravitational wave is the first thing that arrives to the detectors, because it's the phase where the 2 stars are going one around the other, and then they become one single star. The one single star is a new star. So the new star can be observed by all the telescopes as well. So if we detect a gravitational wave from this kind of signal, we can call all the telescopes around the world and say, hey, telescopes, let's go there and go in that direction and explore that direction and see if there is a new star which was born. And this was actually the case on the 17th of August of 2017. And now we will see this movie, and I will tell you more about this thing. Now I leave the translator maybe to read, if the translator can see the image. It's the usual thing I said so far. So here, as you see, the first thing which arrives is the gravitational wave, which is this signal here. And then all the telescopes around the world started detecting the electromagnetic signal. And here what you can see is the electromagnetic spectrum and the light detected by these telescopes here, like at which wavelength this signal was detected. So what happened was that in this system, at some point, there was a very small star which appeared at the top left of this system, and all the telescopes were able to see this new star. So the reason why this is so important is that if you follow the born of a new star since the beginning, you can follow the formation of all the elements one after another, and the indication is given by what is emitted by the light, by the wavelength of the light that you get. Okay, to be continued, hopefully. So, the strength of these of this thing, which really started a completely new way of making astronomy, is that in this way we can point to the source, because we have the localization. We have different signals, so we can localize in the sky where this signal comes from, and we can ask all the telescope to point there. And following all the phases of life of the new star, we understand when the elements were formed. And so, one of the news that maybe you heard is we understood the origin of gold. So why is it that? Because the merging of these two stars was very fast, was something really, really fast. And this explained when some of these heavy elements were formed. So to be clear, let's start with the main elements, hydrogen and helium. These elements came out from the heat of the primordial universe. So at the very beginning, these were the two elements which were formed. And then after this, all the elements up to iron were formed in the nuclear reaction inside the stars. But it was not so clear when all the other elements, all the heavier elements were formed. And so thanks to this discovery, we understood that during this process of formation of a new star, starting from neutron star, also gold, which is an element heavier than iron, can be formed. That's why we said we discover gold, and there were people already ready to go in the universe to search for this gold and bring them home, bring it home. Okay. So here is just a summary of all the signals that we detected in the first two observation runs. We had, as I said before, we are in the third, so there were two before. And this was, all the results were published in a catalog, which includes 10 events coming from black holes and 1 event coming from binary neutron star. So the novelty of this new observation run is that when we think that we see a gravitational wave, we don't keep it for ourselves, but we spread the news. We spread the news also on the social media. For instance, there is my mother, which sometimes calls me and say, "Hey guys, compliments, you saw another gravitational wave." And she knows before me because she follows on Facebook the LIGO Virgo collaboration, and she knows when gravitational wave happened. So besides that, besides the social media, the important thing is that also data are public, they are shared, and so also other groups which want to make some analysis on gravitational wave, on this data, they can do it, and maybe they can find some more, they can try and find something. So there is this public page, so if you follow us on Twitter, Facebook, wherever, you can actually know when gravitational wave arrives. And then you also know what is the probability that there is this source rather than another source. Of course, they are, let's say, candidate events. And so far, since the beginning of 03, which was in April, we saw 26 candidate events since the beginning up to the 1st of September. That one was the last one. So more or less 1 per week. And so I will leave you with this sentence by Stephen Hawking. Because, you know, if I want to start telling you all the possible consequences of this discovery, it will take forever. But I think that this sentence summarizes very well. And I hope the translator is reading it. It's done? I don't want to superimpose to the translator, that's why. So, I mean, this is a completely new observational window on the universe. And we hope we can have more and more discoveries like that, and even better. So again, if you want to follow us on the social media, you will get information, maybe not every day, but every time we will have a signal. And also you can come and visit us in Virgo, as I said before. And thank you for your attention.
Teraz można zadawać pytania. Pytania można zadawać zarówno po polsku, jak i po angielsku. Questions.
Yeah. Yeah, just a second.
Proszę.
So I have a question. Do the gravitational waves interfere with other waves in the universe, such as light or electromagnetism? And does it make it harder to see the actual gravitational waves?
Yeah, I will reply to your question as soon as I...
Okay.
Anyway, the answer is no. Just to give you an anticipation. Okay. Fine. I'm alive. This is easier. Okay, I can reply to this question first. So, so gravitational waves are very weakly interacting with the matter, and so no, there is not an interference between electromagnetic signals and gravitational waves. They are two separated kind of effects and kind of things, and they do not interact with each other. So if we say we have to reduce noise in the detector, it's just because there are some noise in the instrument which can cover the effect of a gravitational wave. But it's not that they interact, and that's why we cannot detect them.
Okay, another question.
Okay, mainly thank you for this interesting lecture. I have a question because I read an article some time ago.
I'm sorry.
Yeah, I'm here in the corner.
Yeah, okay.
Yeah. I read an article and it was written that the black hole which is placed in the center of our galaxy started to generate some beams of energy, started to blink. Do you have any information about that?
Can you repeat? The black hole at the center of the galaxy?
Yeah, the black hole which is placed in the center of our galaxy started to generate some beams of energy, started to blink.
I mean, if it does, for sure we didn't see anything so far from the point of view of gravitational waves. So I didn't read the article you are talking about, so I cannot, let's say, answer properly. But this is not, I mean, we didn't see any effect from that in particular.
Maybe one question. I have a question regarding the shape of the response between when you crash two black holes, there is a different shape of the gravitational waves, and when you crash two neutron stars, what make a difference? Because everything should be a matter only of mass, and black holes have a much heavier mass. Yeah. And we should see the stronger and longer signal.
Yeah. So let's say the answer to this question is also related to the way the analysis of the data is done, which means to extract the signal from the data. If you see the real data of the detector, it's not at all like this. It's not at all what I showed you. It's something like noise. And you don't see by eye the signal. And to see the signal, you have to match the noise of the detector with some model. So some model means that you solve Einstein's equations with different methods, which can be from the analytical methods to numerical methods and so on and so forth. They are very difficult to solve in the phase where the two stars merge into each other, because it's very easy to find a gravitational wave far away from the source, but if you go very close to the source, it's very difficult to solve the equations. So in the end, what you do, you have all the gravitational waves coming from different kind of masses at different distances and so on, and you have a database of all these gravitational waves. And what you do is you match the data with this database until you find the gravitational wave, the signal which corresponds the most to what's inside. Sorry? To the theory. Yeah, to the theory, yes, yes. No, that's true, you're right, because it's also true that there are different theories which go beyond the general relativity, and you can also see that actually what you expect, the signal that you see is slightly different from what you expect, but matches better another theory. And so, because the matching is never 100% point by point. And you can also see that actually the deviation from the general relativity, which can be very, very small, there is actually, and it corresponds to some other theory. So it's a good question, of course. They are masses, so the wave is a wave. But there are small, very, very small differences in for instance, the amplitude, and at the same time the period, and when does the final part come from arrive, so when does the merging arrive, and so on and so forth. So all these small things which seem meaningless actually make a huge difference in the search of the sources.
I have two questions. One is why the interferometers only now can find those waves. Is it only a matter of their size?
No, it's a matter of their sensitivity. Because so far, so you have to imagine the interferometers as a machine, as a radio, or I don't know. Yeah, let's imagine a radio, but you are increasing the volume slowly, which means we are increasing the sensitivity of our detector with new techniques. So it's not straightforward to reduce all the noise sources. And so far, in the last, 30 years or so, maybe even more, the problem was to reduce this noise source. So I didn't put anywhere the sensitivity of the instrument because I thought it was too technical. But the sensitivity of the instrument is something like a curve, which is the noise above which we can see the gravitational wave, but below this noise we cannot see the gravitational wave. So what we work on every day is we try to push this curve down and down in such a way the signals that we can see are more and more. So it's a matter of sensitivity of the instruments and of the techniques used to improve this sensitivity.
Mm-hmm. And second, you mentioned that in 2017 the gravity came first, and then everyone in the world could focus their laboratories on magnetic waves. So why the electromagnetic waves were slower? What was the reason that they were later on in our places in the Earth?
It's maybe I didn't explain it properly because. Of course, electromagnetic waves arrive at the same time, but the telescope cannot point all at the same time in one particular region until you tell them go there, because telescopes usually go around in the sky and search for something. But only when you tell them go there in that particular region of the sky, of the universe, in that case they can point all together and see all the electromagnetic emission afterwards. Okay? It's not that it was not present before, because there were electromagnetic emission also before, but nobody was there looking. So the strength of this thing is that you can tell everybody where to look and when. Because otherwise, most probably miss the signal. Because this signal is, this kind of star can be very, very small, very, very tiny, and you never catch them. I mean, it's rare to catch them with the telescopes.
Okay, so when you observe the waves, you can, based on the wavelength and all the properties, you can assume what has happened. But my question is, can you know it before and anticipate that, okay, this, what I'm registering, is this particular an event in the past, or you learn about the events from the past based on those wavelengths?
So if you understand, your question is, like, you can, okay, let's say like this. If you have telescopes, if you have one telescope which observed a binary system which is starting spinning, in principle, so let's say imagine that you have a system of binary neutron stars that you can see with a telescope, and you follow this orbit. And in this way, you are able to predict when they are going to merge into each other. So usually, it's very difficult to observe these kind of things and know that they are going to finish right after. I mean, I should explain it better. So if you have neutron stars doing this job, probably when you see from when you see it from the first time, the final event will happen in, I don't know, maybe a century or so. So maybe you can also predict when the gravitational wave will happen, but most probably the time for it to happen will be very long. Because I didn't say that, but it's very, we cannot see all the sources with these detectors. Of course, we are developing also other detectors more sensitive and more sensitive also to other sources, because now we are mainly sensitive to supernovae explosion, neutron star, binary neutron star coalescence, and black hole coalescence. But all the other sources, so far, we cannot see them with these detectors. And we need different kind of detectors to do it. So usually, although I'm not an astrophysicist, so I cannot be so specific, but usually when you see this kind of sources with a telescope, it's difficult, the coalescing sources, it's difficult that they are going to finish right after, and you can tell gravitational waves. Maybe one thing that you see is pulsar stars, because they spin on themselves and they also make gravitational waves. So these kind of gravitational waves, yes, you can see them. And so you can be alerted by the telescopes. So the telescopes will tell you, okay, at this frequency, you should find the gravitational wave from this pulsar. So this is one of the possibilities.
Hi, can I, here on the left. I also have two questions. First one, I'd probably repeat the other one, because from what I understood, the observation of the event in electromagnetic waves is delayed to the gravitational waves event. Is it not?
No, it's not delayed. It's just that we told telescope to look afterwards.
So, but it's afterwards, after the merger has already happened.
Yeah. So maybe we can put again the slide, guys on the top. Yeah, okay. So if you go back to the slide back, I'll tell you when you stop. Back. Okay, now, further. Yeah, this one. So if you scroll the movie a bit, can you do it? Go ahead. So I will show you what I mean. Okay, we will watch it again. So meanwhile,
so both, they actually do move at the same speed?
Yeah. Yes. And now at the bottom, what we will see is, first of all, in the first, at the left, to the left, we will see the gravitational wave, and then the axis is the time. So wherever no, it's not the time, sorry. But it's just to say, this is what happens first, gravitational wave. And then after, we say, okay, telescopes, go and watch there. And after this, telescopes will start detecting this stuff. But at the same time as the gravitational waves, there were electromagnetic waves, but nobody was watching.
Okay.
That was.
So my other question, you said that the events happen on average once per week. How does it compare to what we were expecting to see?
Yeah, so the expectations were a bit different, mostly with respect to black holes, meaning that we expected less black holes than we actually found. And at some point, we got bored of these black holes. Okay, another black hole. So that's true. There is a difference with respect to the expectation, but the theory to explain why it happens are still ongoing. See, yes, yeah.
And I have a question. What are your thoughts and expectations concerning the dark matter and observing dark matter with this? Because I think it appeared in one of the first slides.
Yeah, I mean, I'm not an expert on this, I would say. So I'm afraid of saying incorrect things. But today, at this meeting, which was held here, I've heard a presentation of an astrophysical theorist, and I mean, this was something new. Maybe it's well known among data analysis people, but it was new for me. So I've heard that, for instance, the shape of the gravitational signal, which was what he was asking about before, this shape can be influenced, the process itself can be influenced by the dark matter presence. So both the shape and something which is called the echo of gravitational wave. These are processes which are foreseen to come from the interaction of dark matter with matter, and so with black holes. There are many processes which are, let's say, this is just at the level of the theory, many processes which can influence the shape also of the signal. And so that's, from my side, that's everything I can say about dark matter and gravitational waves. Then I don't know if there are many more implications. This is not my field, I'm sorry.
I have a question. Is it possible to bend gravity waves? I mean, to build a kind of lenses for gravity waves, to focus them, or to manipulate in some ways?
Okay, the only way to bend the space-time, because gravity waves are space-time contracting and stretching, okay? And so what you want to do in practice is to bend the space-time itself. And so the only way is to put mass or energy. So that's why you try to make an analogy with electromagnetic wave, but it's a bit more complicated because gravitational waves are the space-time itself changing. And so your question can be rephrased like, can we bend the space-time? Yes, I mean, no, because we cannot make a black hole ourselves, but the only way to bend space-time is to put a huge concentration of mass or energy.
Okay, I wanted to ask which kind of noise posed the biggest challenge to reduce for the interferometer? Was the seismic one, or the thermal one, or the laser characteristics one?
All of them. All of them.
All of them. There was no singular most difficult one to work around.
All of the noises are tough to deal with, meaning that also, I should be more precise, not all the noises are at the same frequency. So every gravitational wave has a particular frequency, which can be, a lower frequency or higher frequency. And this is what determines the bandwidth of a detector. So the detector can be sensitive in a certain bandwidth, depending on the frequency. So for different frequencies, you have different noises. And some of the noises, of course, can be in the same frequency band, but all of them act in a different band. And so all of them are tough.
To jeszcze jakieś 2-3 pytania. Prosimy dalej.
Could you tell me something about changes in time which are observed with a gravitational wave? Because we can observe some changes in our space, but also in our time.
Yeah, so it's true. It's a complicated question. So let's say for what concerns the interferometer, which is what we use to detect gravitational wave, we are not really sensitive to, let's say, for the way it works, we are not sensitive to the change in time, but just to the change in length. And so we consider the speed of light, of course, constant in the two arms of the interferometer, and whatever change in time for the way the interferometer works is, let's say, it's overcome by the way the interferometer works. So it's true that there is a change in the space-time, but we detect the change in space in this way.
I have a question. What discovering of gravitational waves may change in our usual life for ordinary people?
Nothing. No. Okay, now I try to be more serious. So, so far, really nothing. So, if we want to look at the impact of the research of gravitational waves on our life, this can make sense, because to make this interferometer so sophisticated and complicated, we need to have technologies which are at the frontier. So they are very, we discover new things, we make new things, we make new technologies, new techniques, and so on. And these, after many years, or after a few years, can also have an impact on our everyday life. More or less, it's the same as it happened for the CERN, if you think, because our life didn't change with or without the Higgs boson, but thanks to the CERN experiment, it was the internet was developed, and so internet is something that now lives with us every day. So for sure, we can think about the technological implication of the research for the detectors. But for gravitational waves themselves, I doubt that we will have mobile phones with gravitational waves. That's for the moment, but who knows?
Would it be a good idea to build detectors of gravitational waves in space in order to reduce noise?
Yeah.
Is there such a project?
Yeah. Indeed, this is a project. And this project is called LISA, and is a gravitational wave detector in space. So it's let's say the principle, the working principle is very similar. Is kind of similar to our ground-based detectors, but of course in that case you have a ray of light, you have a laser which travels for million kilometers. I don't even remember how long is the arm of LISA. Yeah, so it's very, very long. And this interferometer is supposed to orbit around the Earth. This is something which, I mean, at the moment we just had some, what is it called, the thing that you go and put in the space? Like, we had some preliminary experiment to have some idea of the noise sources. This worked pretty well, and people are really optimistic about this, and so this project is going on. Yes, Pathfinder, yes, Pathfinder. I didn't find the word, yeah. So the Pathfinder, it happened maybe 1 year ago or 2 years ago, yeah. And they found very successful results, and so the project is going on. And the sensitivity in frequency of this kind of instrument will be a bit different with respect to the Earth-based detectors, meaning that the kind of sources that it can detect are different, slightly different from what we see now. That's one point. And also, the nice thing is that you can see, for instance, the signal coming from black hole spinning, And this is a trigger for the Earth-based detector because if you see this signal, you can predict the waveform and when they're going to finish, what you were asking before. And so you can tell the Earth-based detectors when they are going to wait for this waveform. So this is a project.
I heard the gravitational wave can help us to learn more about the Big Bang. Was anything discovered in this subject?
Not yet, but this is one of the implication of the research on gravitational waves, because among all the sources that I listed, there is one which is called the stochastic background. So stochastic background means there are gravitational waves from many objects which happened anytime in the universe, but also there are echoes from the Big Bang. And so this is something which we are also looking for, but to catch this kind of signal, we have to still increase our sensitivity. So far, it's not yet the case that we can actually detect it, but this is, of course, one of the main aims. We can discover much more about the Big Bang, the starting point of the universe.
Dziękujemy za odpowiedzi na wszystkie pytania, za interesujący wykład. Jeśli ktoś jeszcze chciałby porozmawiać z naszą prelegentką, to będzie można to uczynić w kuluarach. Jeszcze jest na to czas, a do 21:30 jeszcze jest czynna wystawa. Można zobaczyć zwizualizowane fale grawitacyjne, jak to w ogóle sobie wyobrażać. Więc kto jeszcze nie widział, w sąsiedniej sali, na zapleczu sali audytoryjnej są różne ciekawe eksponaty do 21:30. Thank you very much.
Thank you.